Now, when we have observed an association between risk factor X and disease Y, we have to take into account the possible explanations for that observed association. And what I'm showing here in this pyramid figure on the bottom part of our slide is that the majority of associations that are observed in science, in epidemiology, are due merely by chance, such that that particular association is a spurious one, and it's due to some random error that occurred in our data or our study. The next most common explanation for an observed association in epidemiology or science is when it's due to bias. And this is also a spurious form of association or type of association. In this instance, it's a bias that's driven by a systematic error, either in our study design or our study conduct or data collection and analysis. And we've talked about random and systematic error already when we've talked about different kinds of bias in the design and measurement in the epidemiology studies that we've discussed in the class. The next most common explanation for an observed association is when there's some confounding going on. And we're going to discuss confounding more in the next set of videos in this module. But confounding is where you have a type of association that's real, but it's being affected by a third factor that's essentially altering the true association, either upwards or downwards. And the explanation for this is when you instead have cause and effect, you really have the reverse occurring. An example would be, the cart before the horse. Then the next example of an explanation for an observed association would be when there's no causal association going on at all. The type of association is real, however, we're measuring it in a way that we're not able to truly conclude that X causes Y. So confounding and non-causal relationships are similar. We will discuss how to identify those in a future video. And then at the top of the pyramid is really what we want to have or show or explain our observed association. This is our goal anytime we do a study. We have a hypothesis that X causes Y, and we hope that when we collect our data and analyze it, that the measured association is truly demonstrative of a causal association. So there's a real relationship going on, and cause does precede the effect. And then finally, the most ideal scenario is where we've done that. We've shown that X causes Y, but that we also can understand why. We can also understand the causal mechanism for why that occurred. So here's an example of those different types of explanations for association using an observed association between coffee drinking and myocardial infarction, or MI. The most common explanation for that association is probably because it was a measurement that just showed an association and it was due to chance. That really coffee and drinking and MI are not related, but we just measured it, or we measured something and we found this positive association, but it's just by chance alone. Then the next most common explanation is that our data or our study had some bias in it that led us to conclude that there's this association, but there really isn't. The third is when there is a relationship, but it's really an issue of we can't decide or determine which came first, the cause or the effect. In this case, we could have the reverse occurring, where essentially MI is the cause of coffee drinking, which could be true, I suppose. And then the confounding scenarios where we do see we measure an association, but that there's a confounding going on by some third factor that we're not measuring or we're not aware of. And then the last explanation would be our ideal explanation, which is what we saw was actually true, that coffee drinking does cause MI. Okay, that's just a way to think about those different explanations in an example where you can kind of think through it. And so here are a few more examples for you that I'll leave you with to think through whether or not these factors are necessary or sufficient or component causes for these particular scenarios. And then this is just a figure to kind of humorize some of these concepts about, is correlation causation, and often the case it isn't, and this is just a funny way of thinking about it in terms of proof of global warming. And then this is an interesting book if you're interested in understanding the current ideas about calories and fat and carbohydrates, as well as, and how those are associated with obesity. And this particular writer essentially argues that we really aren't, obesity isn't due to overeating, but it's really the other way around, that we're overeating because we're obese. And it has to do with this idea of needing fuel to power the body once the body's of a certain size. So I won't go into this greatly, but it's another example of where the relationship between an effect and an outcome could actually be reversed from what we think is true. So I just want to briefly walk through some philosophies about scientific inference, and I'm going to go through this really quickly. This is just hopefully a refresher from some of the information you've learned in the past, maybe in a biology course or a philosophy course, but thinking about different ways of scientific inference. So you have what's called inductive reasoning, or inductive reasoning. And this is this idea that scientific reasoning depends on making some generalizations or inductions from observations to general laws of nature, and that those observations are said to induce the formulation of the natural law in the mind of that scientist making those inductions. Now, Hume criticized inductive reasoning because he said it follows no logical force. And he's true, but unfortunately, inductive reasoning is still used today. It's what we use in science, so called the scientific method, where we take the form, we know that if H is true, B must be true, and we know that B is true, therefore H must be true. There's also circular reasoning exploration, and this is the idea of X causes Y, so Y causes X. So again, it's a very circular approach to thinking, and it's not a valid way to think. And here are some cartoons to kind of humorize this concept. Also in scientific inference, there's conjecture and refutation, and this was established in 1934. This is the idea that scientists form hypotheses based on intuition, conjecture, and previous experience. Good scientists use deductive logic to infer predictions from the hypotheses, and then they compare observations with these predictions. Hypotheses whose predictions agree with observations are then confirmed. This is the idea of corroboration. The problem with this particular approach is that science proceeds in the opposite direction, right? We begin with a scientific theory or conjecture, and then we conduct an experiment, and then we eliminate those theories that are falsified by the results that we obtain from that scientific experiment. And then there's what's called consensus and naturalism, and this is an idea that's established in the mid-1900s, and it's still in effect today. And this is where the role of the scientific community essentially is involved in judging the validity of scientific theories. So essentially science follows some sociologic process. And for better or for worse, this type of thinking and scientific inference is still, as I said, used often in today's scientific world, right? We have consensus bodies, we have expert communities that come together and put together guidelines for various purposes, and it's driven by consensus. And there are pros and cons to this, and one con is that it can kind of follow this mob mentality, and thus somewhat of an irrational process. And then the last idea about the last, topic in scientific inference is that was established by Reverend Bayes in 1700s, and it's called Bayesianism or Bayes theory, and this is hopefully something that's not new to you. But the idea of Bayes theory is, and this is how we really think as human beings, we have some a priori hypothesis about something, conduct a scientific experiment, and then we refine our prior hypothesis using that information, and we generate what's called a posterior probability. And again, this is really the way that we think in science. This is the way healthcare providers often think. An example would be a patient comes in to see their provider, and their provider does a history and takes information from that patient, and then that healthcare provider uses what he or she knows from prior patients who have had similar complaints or histories to then kind of infer as to what the problem is with this new patient.